We will begin this presentation by discussing the assumptions that we have to meet in order to make inferences about a population mean. And then we will learn how to proceed when some of these assumptions are not met. In other words, we will learn how to use the t-distribution instead of the z-distribution when computing confidence intervals and when conducting tests of significance with one sample. We will also learn a new type of test of significance, which is called a matched pairs t procedure, and how to do this by hand and by using software. We already know that when making inferences about a population mean, we make several assumptions. That our sample was randomly selected, that the data have a normal distribution, and that the population about which we're making inferences is much larger than the sample, at least 20 times larger. For instance, let's say that we want to study social skills in girls with Asperger's syndrome who are 12 years old, come from single parent families, and have no siblings. So the total number of individuals who meet all of these conditions is quite small. Because the population that we're interested in is so small, our sample may not be 20 times smaller than the entire population. Also, sometimes the sample is very large and actually includes the entire population, like the standardized achievement tests that are administered to every student in the state. In this case, we don't need to compute a confidence interval for the population mean, for instance, because we know the population mean. Our population is represented by all the students in the state. When all of these assumptions are met, and we know the population standard deviation for our variable, we can use z-scores in the computation process. However, many times these assumptions are not met, and even more often we don't know the population standard deviation for our variable. In this case, instead of using z procedures, we're using a different set of procedures that are called t procedures, which are based on a distribution of standardized scores that are called t-scores. T procedures are very similar to the z procedures, and they are used when the data are not perfectly normal and when we don't know the population standard deviation. Because we don't know the population standard deviation for our variable, with t procedures we use the standard deviation from our sample instead. The notation is different now. Instead of sigma, we now use a lowercase s. The formula, however, stays the same. In both cases, we divide the standard deviation by the square root of the sample size. The only difference is that instead of using the population standard deviation, like we did with the z procedures, we're now using the standard deviation from our sample. And the result is called the standard error. The interpretation of this statistic is the same. If we had many random samples and for each one we computed the mean, the standard error would show the average distance of these sample means from the population mean. After we estimate the standard error, we can compute confidence intervals and conduct tests of significance. For this, we use the same formula as we did with the z procedures, but we use the sample standard error instead of the population standard deviation. The other difference is that we now use the notation t instead of z. So we have a t star instead of a z star in the confidence interval formula, and a t test statistic instead of a z test statistic for the test of significance. The interpretation of t-scores is the same as the interpretation of z-scores. They are a standardized measure of how far a sample mean or a certain given value is from the population mean. However, the distribution of t-scores has a slightly different shape than the distribution of z-scores, which is a normal distribution. The distribution of t-scores is symmetric, but is not normal. In this figure, the z, or the normal distribution, which is represented in blue, and the t distributions, which are represented in different shades of pink, are overlapped to be able to compare them. Like the normal distribution, the t distribution has a single peak and a mean of 0, which is the center of the distribution. But the tails of the t distributions are higher, are fatter than for the normal distribution, and the distribution has more spread. There is more spread in the t distribution because the standard error is larger than the population standard deviation. There is more error in this estimation. Therefore, when we use t-scores to make inferences, we have a little less precision than we do with z-scores. This is the trade-off for being able to use these scores without meeting some of the assumptions. Another important distinction is that the t distribution looks different for different sample sizes. You can see in this figure that as the sample size increases, the t-curve gets closer and closer to the normal curve. This is why when we are using t-scores, we have to take into account the sample size. In computation, the sample size is specified by the number of degrees of freedom, which is equal to n, the number of individuals in the sample, minus 1. T-scores can be used just like z-scores to compute a confidence interval for a population mean. To obtain the upper and the lower limit of this confidence interval, we add and then subtract the margin of error from the sample mean. As we mentioned before, instead of using the population standard deviation, we are now using the sample standard deviation. And instead of z star, we are now using t star in this formula. T star is also called a critical value, and just like z star, it can be obtained from table C in our textbook. Also, this type of confidence interval can be obtained using statistical software. As we mentioned in the previous slides, the shape of the t distribution differs based on sample size. Therefore, for the same confidence level, the value of t star will be different for different sample sizes. This is why when we use table C, we must know the degrees of freedom for our sample, which can be easily obtained by subtracting 1 from n. For instance, if we have 12 individuals in the sample, the degrees of freedom will be 11. When using table C, the different rows specify the degrees of freedom for our sample. In our case, df is 11, so we are looking at the 11th row. Then we move across columns until we find the column that corresponds to our confidence level. In this example, we have a 95% confidence interval, so the value that we're looking for is 2.201. This is our t star. Notice that for the same confidence level, the value of z star is 1.96, a little smaller than t star. So the margin of error with the z procedure is a little smaller than with the t procedure. This is the price that we pay for not meeting the assumptions that are needed for the z procedures. So in case you are wondering why we're not using t procedures all the time, since they don't need to satisfy many requirements, this is why, because they are slightly less precise than the z procedures. This example shows how to compute a t-confidence interval by hand. Let's say that we would like to estimate a population mean on a student achievement motivation scale. We have a sample of 61 students. We administer the scale, and the mean score on this scale is 100, and the standard deviation is 15.62. We want to estimate a population mean with a 95% confidence level. Because we don't know what the population standard deviation is for this scale, we are going to use the t procedure instead of the z procedure. The first step is to obtain from table C the value of t star that corresponds to the confidence level and sample size. So to find t star, we must first have to compute the degrees of freedom, n minus 1. So df in this case is 60. And if we look in table C, when df is equal to 60 and the confidence level is 95%, the value of t star is 2.000. If we replace all these values in the confidence interval formula, we obtain a margin of error of 4 points, which we will then subtract and add to the sample mean of 100 to obtain the lower and the upper limit of the confidence interval. The lower limit is 96 and the upper limit is 104. So we can say with 95% confidence that the population mean on this motivation scale is between 96 and 104. These results can also be obtained with statistical software, but if we don't have the actual data, just the mean, the sample size, and the standard deviation, we can also do this by hand. Also, knowing how to do this by hand is important for being able to understand and interpret the results provided by statistical software and to detect potential errors when the results don't make sense. As we mentioned before, t-scores can also be used to conduct tests of significance, just like z-scores. The null hypothesis, HO, is the same. It states that the sample mean is equal to the population mean, or that there is no significant difference between the two values. Also, the alternative hypothesis is formulated the same way. It can be one-sided, stating that the sample mean is either lower or higher than the population mean, or it can be two-sided, stating that the sample mean is just different than the population mean, which means that we have to test for both very high or very low values. Similarly, the formula for the t-test statistic stays the same as for the z-statistic. The only difference is that instead of the population standard deviation, we now use the standard deviation from the sample. Also, the value of the t-statistic differs based on the sample size or degrees of freedom. After we compute the test statistic, we use this information to determine whether the null hypothesis should be rejected or accepted, just like we do with the z-test. The p-value for the test statistic can be obtained using statistical software. The table in your textbook does not provide p-values, but we can still use the information in table C to decide whether we should reject or accept the null hypothesis. And we will see how to do this on the next slides. This example illustrates how to conduct a test of significance using the t-statistic by hand. We can also do this using statistical software and obtain the same results. Let's suppose that we know from prior studies that the population mean for the motivation scale that we mentioned earlier was 94, but we want to challenge this statement to see if it still holds true. So the null hypothesis is that the population mean is equal to 94, and the alternative hypothesis is that the mean is different. It is a two-sided alternative hypothesis. The first thing that we should do is to collect a sample, which in this case has 61 individuals, and then we compute the mean for our sample, which is 100. Because we don't know the population standard deviation, we have to conduct a t-test instead of a z-test, and use the sample standard deviation, which is 15.62. We also have to specify from the very beginning the value of alpha, our significance level, which is 0.05. If we replace all the information that we have in the t-statistic formula, we obtain the value 3. And we can see in the figure approximately how far from the mean this value is located. So the next step is to determine whether this statistic is far enough from the mean to reject the null hypothesis. As I mentioned on the previous slide, after we compute the test statistic, We have to determine whether this score is far enough from the mean to reject the null hypothesis. If we're using statistical software, the p-value for any value of t is computed for us. And if the p-value is lower than alpha, then we should reject null hypothesis, just like we do with z-test. When we're not using statistical software, we can use table C in the textbook. However, in this case, the procedure is a little different than what we've done so far. Because table C does not provide p-values, it gives the value of the t statistic at different probability levels and for different degrees of freedom. Therefore, after we computed the test statistic t for our test, we must find the t-score that corresponds to our alpha level, which is called the critical value of t. And this will be our cutoff value for t. So if the t statistic is larger than the critical value, then we can reject the null hypothesis. If the test statistic t is smaller than the critical value, then we should accept the null hypothesis. Let's find the critical value in table C first. The last two rows in the table show different values of alpha, or different significance levels. If the alternative hypothesis is one-sided, then we should use the row for a one-sided value. If the null hypothesis is two-sided, then we should use the row for the two-sided p-value. In our example, the alternative hypothesis was two-sided, so we should use the two-sided p-value. And we look across columns for the value 0.05, which is our alpha. After finding the 0.05 column, we move up across rows until we find our degrees of freedom, which in this example is 60. So the critical value that we're looking for is 2.000. Our test statistic was 3, which is larger than the critical value, which is 2. In this case, we reject the null hypothesis because t is further away from the mean than the critical value. It is beyond the limit or beyond the cutoff level. When t is smaller than the critical value, then we should accept the null hypothesis. Everything that we have discussed so far in this presentation was very similar to what we learned about Z procedures, with some modifications. The t-distribution is also used for a different type of statistical test, which is called a matched pairs test. Many times in social science research, we need to compare two equivalent groups to assess the effectiveness of a certain intervention, or even more often to compare the results of the same group before and after a certain intervention. In such situations, we have what is called a matched pairs design, because the two groups or samples that we work with consist of either the same individuals or individuals who are very similar. With the before and after study, the pairs are represented by two values that are recorded for each individual's before and after a certain intervention. This is an example of pair data. We have a sample of 20 students, and for each student we recorded the score on a pre-test, which preceded instruction, and a post-test, which was administered after instruction was delivered. Each pair consists of a pre-test score and a post-test score for the same student. What we're interested in here is to determine whether there is a significant improvement from pre-test to post-test. The third column in the table shows the differences for each individual between post-test and pre-test scores. The average difference for the entire sample is 10.05, but just by visually inspecting these differences, we cannot tell if they are statistically significant. In such a situation, we also have to conduct a test of significance. Our null hypothesis for the test of significance is that in the population, The average difference across all individuals between post-test and pre-test is equal to 0, so there is no significant difference between the scores on the two tests. Notation typically used for the population difference is mu d. Because we are expecting to see some growth in student achievement from pre-test to post-test, the alternative hypothesis is that the difference is in fact larger than 0. When for any reason you expect a decrease, then the alternative hypothesis should specify that the mean difference is lower than 0. For instance, if you measure the incidence of behavior problems, you may expect a decrease after an intervention was implemented. But we have no idea whether scores should increase or decrease. The alternative hypothesis will be two-sided. The data recorded from this sample shows that the mean difference is equal to 10.05 and the standard deviation of these differences is 7.56. Because we don't have the population standard deviation for this difference, we're going to use the t-test of significance. The formula for the test statistic stays exactly the same. X represents the mean difference from the sample, and mu d is equal to 0. If we replace all the values in the formula, we obtain a test statistic that is equal to 5.94. If we are using statistical software, we can automatically obtain both the test statistic and its p-value. When t is equal to 5.94, calculators or statistical software show that the p-value is equal to 0. This value is obviously smaller than alpha, which is 0.05, so we can reject the null hypothesis. Statistical software provides the two-sided p-value, so if the alternative hypothesis is one-sided, we just have to divide the provided value by 2 to obtain the value that we are looking for. If we use table C instead of software, we first have to find out the critical value of t for 19 degrees of freedom and the two-sided alpha of 0.05. The critical value is 1.729. The test statistic, which is 5.94, is larger than the critical value, so we can reject the null hypothesis. In conclusion, based on the evidence from our sample, we can say that the difference between post-test scores and pre-test scores is statistically significant.